Welcome to AP Podcast 14.2. This podcast is on acid strength. And what we're going to do is try and make sure we've got a good understanding of the difference between strong acids and weak acids. If you talk to the average person on the street, they go, ooh, acids. And what we're going to do is make sure that we know the difference between the two. So I've got from this the set of bullets right here, you can see from this set of bullets and this set of bullets, I've got a simple comparison of the two. Okay, we've got strong acids and weak acids. Now, if we think of the equilibrium constant for strong acids, Ka is very large. And hopefully that makes sense to you because you know when a strong acid breaks up, it breaks up completely into ions, right? And so the equilibrium really lies to that side. It's very product favored. And so if you think about the concentration of the H ion concentration to whatever the concentration of the acid, it's 1 to 1, all right? And then since the H plus is not, of course, attracted to this A minus, water is a stronger base. Now, if we look at a weak acid, think about it this way. If we take a weak acid, this equilibrium really lies that way. In fact, this anion right here has a very high affinity for the H plus ion, and so therefore it's really floating around as HA. And I think the book talks about 1 in 10,000 molecules will break up. So the Ka is very small, and the concentration of H plus is a lot less smaller than the concentration of the acid. And the reason for this is that the anion is a much stronger base, a base being a proton acceptor, than water. All right. Now this is a review right here, but there are the 7 strong acids that I asked you to learn way back when in Chapter 4. And again, the little saying goes hibber hickle high, hono hoso hickalo, just as a way of remembering it. But again, it's always good to remember those strong acids because they pop up so often. So let's look at a problem from our book. And here we've got, consider the following illustrations. Now in this jar we have right here, the jar on the left, you could see everything's broken up, right? And on the right you could see that everything's bonded. So obviously what's happening is this is representing over here the weak acids, right? And over here we're representing the strong acids. So this problem is relatively simple. All you've got to do is decide which of these are strong acids. They would go in that beaker, and which are the weak acids, they go in that beaker. So let's look. Strong acids, nope. Here's a strong acid, there's nitric, there's hydrochloric, there's a strong acid, and the rest are weak acids. So these two go right up there. Those all go to that one right there. All right? So hopefully that makes sense to you. Strong acids and weak acids. Now, when we look at weak acids a little more carefully, we know that the equilibrium lies far to the left, and if you have that solution floating around, you have a much stronger conjugate base. All right? And this is going to play a big role down the road in this chapter. If we have the acetate ion floating around like that, and it happens to be sitting in water, well, guess what it's going to do to one of those water molecules? It's going to rip an H off and make the acetic acid molecule. And that's going to be a very, very important thing. But when you think about weak acids, you want to really focus on the fact that the anion is a very strong conjugate base, because that stuff is going to play a role in a lot of our chemistry coming up in the future. All right? So we've got strong acids and weak acids. Well, let's talk a little bit more about the type of acids that we have. You've got a number of ways to describe them, but a monoprotic acid is one that has one proton. And so if I ask you to draw that, basically you're thinking about things like HF, that's a monoprotic acid. HCl, that's a monoprotic acid. So we're talking about there's one proton or one H plus to be donated from that molecule. A polyprotic, now that's going to have more than one. Well, what is the most common polyprotic acid we see in class? Good old sulfuric, right? This thing has 2 H's to donate. All right, and then really the only triprotic acid that you see on a regular basis in class is good old phosphoric acid. There you can see it's got 3 different H's it can donate, or 3 different protons it can donate. So those are some terms that we got to make sure we keep straight. Now, as far as oxyacids, well, hopefully that makes sense to you. It's going to be an acid that has oxygen, and there are 2 right there: sulfuric, phosphoric, and basically, if you think of any polyatomic ion that has oxygen, and you put a few H's in front of it, then you have a oxyacid. Now, the other acids that we see in this class, but we don't use very often, are the organic acids. All right, and mostly they have a carboxyl group, and all the carboxyl group looks like this. Some organic chemistry you guys have a chance to look for, but oftentimes you'll see acetic acid written like this: CH3 COOH. And we've called that Kachu or whatever. And it looks funny to us because we're so used to writing the acetate ion as oops, let me get over here, as C2H3O2, right? It looks funny to write this, but organic chemists will write this out like this just to designate that functional group and help with keeping track of the chemistry a little bit. All right? So we've got our acids and bases, our type of acids. The next thing I want to look at is the fact that water tends to be an acid or a base, which sounds kind of odd to you. It probably does sound kind of odd to you anyways. But what we have is water is amphiphoteric. There's a nice little Jeopardy word you might see sometime, amphiphoteric. And all that means is it behaves both as an acid and a base. And then the other thing about water is it autoionizes. What in the world? Oops, autoionizes. Well, all that word means is that it will just be sitting in a, imagine sitting in a beaker or maybe your water bottle, and it's just going to, as it's sitting there, it is losing a hydrogen to become an H3O plus and becoming an OH. All right, and so, but let's look at this, right? That means we have an equilibrium. Okay, so it is an equilibrium, and the fact that it does autoionize is important. But look at the amount that it does. Look at the K. 1 times 10 to the minus 14th, which is really, really small, right? So which way does this equilibrium lie mostly? Well, it's heavy to the reactant side, correct? Now look at this. KW. Holy cow, Mr. Richardson, that's another K. Yeah, it's a K, but it's the K for water. So if you put the products over the reactants, right, and notice we have a liquid right there, so we can't put, liquid on the bottom. So the KW, the equilibrium expression, is just really H plus times the concentration of OH, right, which is what I have there, and it equals 1 times 10 to the negative 14th. So that's important to remember. And that's important to remember this bullet right here. That happens in every aqueous solution. In other words, any kind of aqueous solution, water is autoionizing to that degree, which, is very, very small, 10 to the minus 14th. That's almost not even something to worry about, but it becomes very important when we start calculating pH. All right. So if we have a neutral solution, and that's a solution where the concentration of the H and the OH is equal, we get a value of 1 times 10 to the minus 7th. Well, if I take those two values, right, and I multiply them together to calculate K, you can see where we get KW, because that number times itself is 1 times 10 to the negative 14th. Now, if we have a situation where the concentration of the H is greater than the concentration of the OH, then that's where we have our acidic solution. And conversely, if we have a situation where the concentration of the H is less than the concentration of the OH, we have a basic solution. And that's going to become very, very important when we start calculating pH, which we'll do in the next chapter. So I've got a couple practice problems I want you to try. So pause the video and see if you can do this. All right, is that what you got? Well, first of all, hopefully you recognize that HCl is one of the strong acids, and it's the only strong acid there, so that's super strong. Then I have to look at the Ka. And again, probably the easiest way to think about it is the bigger the Ka, the stronger the acid, right? So HF has a Ka of 7.2 times 10 to the minus 4th, so that's bigger than 1.6 times 10 to the negative 10th. So this would be the second strongest acid than that one. And then what's the Ka for this one, or really the Kw? Right? Equals 1 times 10 to the minus 14th. Oops. So there you go. So as far as acids go, that's water's the weakest acid. All right? Hopefully that makes sense. Let's try another one. Look at this one. Pause the video. See if you get what I get. All right, is this what you got? Well, let's just quickly go over this. We've got the anion of a strong acid, right? So you know the anion of a strong acid is its conjugate base is incredibly weak compared to water, so water wins. Now, NO2 is the anion of a weak acid. So weak acids, remember, fight more strongly for the H plus than water, and therefore NO2 is going to be a stronger base. Again, have an affinity for an H plus. And then last but not least, look at these two acid strength. HCN is a stronger acid than this thing, right? Not by much though, you can tell it's not by much. But since this is a stronger acid than this one, then therefore its conjugate base would be weaker. And so this right here is a stronger base. All right, hopefully that's making sense. I think I have one more for you to try. Let's see. Nope, in fact, we're going to be done with that. And so again, hopefully this makes some sense. We'll talk about it in class, and see you next time.